And how the Higgs field works, we have to first understand what our best theory describing all the matter in the universe, the standard model of particle physics, is trying to tell us. This theory describes all fundamental particles in the universe as excitations in quantum fields. So for example, an excitation of the electromagnetic field would be a photon. An excitation of the electron field is an electron. And an excitation of the quark field would be a quark, etc. These are waves, but when they are well localized, as in a measurement, they appear to us as particles. These fields span all of space-time in all directions. The animation you're seeing here is a 2D representation for visualization, but the fields would be in 3 dimensions. Every type of matter and force particle has its own field. So all the fundamental particles of the standard model would be represented by different fields. All these fields, when they are in their ground state, that is their lowest energy state, even when no excitations or particles are present, always have some vibration. Due to the Heisenberg uncertainty principle, particles are constantly being created and annihilated. These are virtual particles that exist for such short periods of time that they cannot be measured. They borrow energy from the vacuum when they are created and give it right back very quickly when they're annihilated. But this flurry of energetic activity for each field collectively adds up to 0 net real particles. Real particles are created only when enough energy is transferred to these fields from some other field to cause an excitation. These excitations are the real particles. And since these are quantized fields, any excitation occurs only in set quantities. So for example, an excitation of the electron field would have to occur in integer multiples of 0.511 mega electron volts, or MeV, which is the mass of one electron. So the field can have energy of 1.022 MeV, which would be the energy of 2 electrons, or any other multiple of 0.511, but not, for example, 0.7 MeV, which would not be an integer multiple of 0.511. But the electron only has this intrinsic mass of 0.511 MeV because of its interaction with the Higgs field. Without this interaction, an electron would be massless. It would have energy, but only in the form of momentum, just like photons. This massless electron would be like a charged photon and move at the speed of light. In fact, without the Higgs field, all the other fundamental particles of the standard model would also be massless, with the possible exception of neutrinos. So the question is, how does this mass come about? To answer this, we have to understand the concept of vacuum expectation value of the various fields. What does this mean? Let's imagine for a minute as if there were no Higgs field. If we then took any of the fields and put them inside an empty box, like the electron field, and if we then weighed that box, we would find that box would have no weight. In other words, the field would have no mass, even though the virtual electrons would be present throughout it. Similarly, all the other fields of the standard model would also have no mass inside the empty box, just quantum fluctuations. But here's the big kicker. There's an exception to this rule, the Higgs field. It's unique because the Higgs field in empty space, unlike every other field, has a net positive mass. Its mass is not 0 in empty space. If we were to weigh the box with the Higgs field inside, it would have a weight. The Higgs field in empty space has a mass. This is called the vacuum energy. A more technical term for this is the vacuum expectation value, VEV, of the Higgs field. It is non-zero. It is, in fact, 246 gigaelectron volts, or GeV. This is just the value that we would expect the Higgs field to have when it is in its vacuum state, or in its lowest energy state. Now, as I stated earlier, quantum fields can interact with each other. What this basically means is that anything that interacts with the Higgs field now effectively interacts with this new vacuum expectation value. And that interaction means energy. And since energy and mass are equivalent, the form this interaction energy takes is indistinguishable from the form of energy associated with a rest mass. So when a fundamental particle interacts with the Higgs field, it gains an energy or intrinsic mass. Without the Higgs field, for example, the electron would be massless, like photons, and travel at the speed of light. However, since the electron is coupled to a field with positive value everywhere in the universe, individual electrons are constantly interacting with this Higgs field. This constant interaction effectively slows the electron down. So, if you apply a force to an electron, you can imagine a sort of pushback from the Higgs field that causes the electron to resist acceleration. This property is what we call inertial mass. The electron's behavior in the vacuum is that of a particle with a well-defined rest mass of 0.511 MeV. This rest mass is determined by the strength of the coupling or interaction between the electron and the Higgs vacuum expectation value. It's like the mass of the Higgs field is shared with any other field that interacts with it. How much mass an excitation or particle in any given field has depends on its coupling constant. The fields of all massive particles are coupled to the Higgs to some degree. The larger this coupling is, the more mass its particles will have. Without the Higgs field, none of the other particles would have an intrinsic mass. The Higgs field is like a thick gravy, and if you try to run a spoon through it, it feels heavy compared to moving the spoon through the air. So every elementary particle with mass interacts with this gravy in some way. The particles of the Standard Model that have mass, such as electrons, quarks, and W and Z bosons, are coupled to the Higgs field, while the fields of massless particles, like photons and gluons, are not. So why are some particles coupled? Meaning, why do some particles interact with the Higgs field while others do not? We're not sure. This just appears to be the way the universe works. The photon happens to be one of the particles that does not interact with the Higgs field, and so it remains massless and moves at the speed of light. The mechanism of the Higgs field giving out mass to other particles is called symmetry breaking. This is a complex subject, but if you want to know more about symmetry breaking, I made a video about it right up here. Now, I should add a note about neutrinos. The Standard Model predicts that they should be massless, but measurements seem to indicate that they do have a very tiny mass. We don't know the origin of this mass. It could be that they also interact with the Higgs, but no one really knows for sure. Now, I want to reiterate what I said at the beginning. The Higgs field is only responsible for about 1% of the mass of all the matter in the universe that we can see. The vast majority of this mass is due to the energy of the strong force, which keeps the nuclei of atoms tightly glued together. Yet, this 1% is essential to have the kind of universe we have. In a simple hydrogen atom, for example, the radius of the electron's orbit is inversely proportional to its mass. In a universe with no Higgs field, a massless electron would have an infinite radius, meaning no atoms would form at all. In addition, differences in particle mass are also responsible for the decay of free neutrons to protons. This is called beta decay. Without the Higgs field, the universe may not have any protons at all. So this tiny 1% mass contribution turns out to be responsible for 100% of the universe we happen to have. I'd like to thank my Patreon supporters who make these animations possible. Thank you very much. I'll see you in the next.